audience who happens to be a past speaker and his colleague. So I'd like to ask Kaustubh to introduce Shashwata. Kaustubh, please go ahead.
Okay, thank you, Nomonita. Is there anyone in the audience who doesn't understand Bengali? কেউ আছে যে বাংলা বোঝে না? মনে হচ্ছে কেউ নেই।
সেটাই
তাহলে কি?
হ্যাঁ, সেটাই মনে হচ্ছে না কেউ আছে যে বাংলা বোঝে না।
বেশ, তাহলে শাশ্বতর সাথে আপনাদের পরিচয় করিয়ে দেওয়াটা আমি বাংলাতেই করতে চাইবো। শাশ্বতর একাডেমিক ক্যারিয়ার নিয়ে বলতে গেলে প্রেসি থেকে শুরু করলে কি করে চলবে? শাশ্বত বজবজের নঙ্গি হাই স্কুলের গর্ব। নঙ্গি হাই স্কুলের সে ছিল এক সত্য যুগ। 2013 সালে উচ্চ মাধ্যমিকের মেধা তালিকায় প্রথম 15-র মধ্যে ছিল শাশ্বত এবং তার স্কুলের আরো 2 বন্ধু। তবু সত্য যুগের আদর্শ অনুসরণ করে শাশ্বত কোনোদিনও রায়ো মার্টিন অথবা ছায়া প্রকাশনীর বিজ্ঞাপন দেয়নি। প্রেসিডেন্সিতে সে ছিল আমার সহপাঠী। এটা আমার পরম সৌভাগ্য বললেও কম বলা হয়। আমার এটা বলতে দ্বিধা নেই যে সহপাঠী হলেও তার অবদান আমার বেশিরভাগ শিক্ষক শিক্ষিকার থেকেই অনেক গুণ বেশি। আমার ফিজিক্সের দৃষ্টিভঙ্গি, ভাবনা চিন্তা যেটুকু গড়ে উঠেছে তার দায় শাশ্বতর। 2016-তে সোনার মেডেল নিয়ে বিএসসি পাশ করে প্রেসিডেন্সি থেকে। তারপর চলে যায় জার্মানিতে ইউনিভার্সিটি অফ কোলনে এমএসসি পড়তে। ম্যাগনেটো হাইড্রোডাইনামিক্স সিমুলেশন নিয়ে কাজ করে সেখানে। এমএসসি পাশ করার পর সোশ্যাল মিডিয়াতে শাশ্বত জানায় ব্যাঘ্র, জড়া আর থিসিস সুপারভাইজারের হাত থেকে এমএসসি থিসিস রক্ষা করা গেছে। 2019-এর শুরুর দিকে ইউনিভার্সিটি অফ কোলোনেই পিএইচডি শুরু করে। 2019-এর শুরুর দিক, ঠিক তো?
হ্যাঁ, মার্চ।
শাশ্বত যদি ভুল বলি সংশোধন করে দিস। তোর গুণগানে কি কি বলতে হবে সেটা তো ভালো করে লিখে দিলি, কিন্তু ডেটটা লিখে দিতে পারলি না। যাই হোক, মজা করছি। শাশ্বত এখন কোলনের পিএইচডি স্টুডেন্ট। কোলনে বসেই তার বর্তমান কাজ নিয়ে সে আমাদেরকে বলবে। শাশ্বতকে নিয়ে যত বলা যেতে পারে সেটা একটা টক নয়, বরং একটা লেকচার সিরিজ হওয়া সম্ভব। আপনারা ট্রামে, বাসে কান পাতলে হঠাৎ মাঝে মাঝে ওর ব্যাপারে অনেক উড়ো খবর শুনতে পেতে পারেন। তার বেশিরভাগেরই সত্যি মিথ্যা বিচার করা কঠিন, তবে কখনো কখনো শুনবেন শাশ্বতর কথা ভেবেই নীরেন্দ্রনাথ চক্রবর্তী লিখেছিলেন, আমরা কেউ মাস্টার হতে চেয়েছিলাম, কেউ ডাক্তার, কেউ উকিল। শাশ্বত গাঙ্গুলি সেসব কিছু হতে চায়নি, সে রোদ্দুর হতে চেয়েছিল। কিন্তু কবিতাটার শেষ ভাগটা সত্যি নয়। অমলকান্তি পারুক বা না পারুক, শাশ্বত গাঙ্গুলি রোদ্দুর হতে পেরেছে। সেই রোদ্দুরের উৎপত্তি, সূর্যের উৎপত্তি, তারার উৎপত্তি, সেই নিয়ে শাশ্বতর বর্তমান কাজ, এবং সেটাই আজকের গল্পের বিষয়। শাশ্বত।
So thank you for the, well, I'm kind of glad that my video is off. I'm not really sure what my current reaction would be. Thank you for the really, really kind introduction. I would in general prefer to speak in Bengali, but I think as academic talks dictate, I will talk today in English. Thanks to Kaustubh, thanks to the whole of Presidency University, especially the students organizing this alumni series, for giving me the chance to talk in today's lecture, today's colloquium. So the topic of my talk is about star formation, and the title is A Star is Born, the Life Cycle of Molecular Clouds. But before I talk about what this presentation is going to be about, I want to spend a moment to discuss what this talk is not about. So this presentation is not going to be about this film. So after I came up with the title, it sounded kind of familiar, and I Googled it, and turns out that there's a film in this name. So if you are here today to listen about this film, I'm sorry, this talk is not about that. On a bit more serious note, this talk is also not about the life cycle of a star, which is in itself very interesting. But today we are not going to talk about what happens to a star after it has formed, but we're going to limit ourselves to only until the star forms from interstellar gas. And we're not even going to get down to the actual star. So the essential physical question that we want to discuss today is, how do stars form? So let's say in the evening you go to your rooftop or you go to your balcony, and unless you live in a huge metropolis like central Kolkata, for example, you can see stars in the night sky, a lot of them. And since antiquity, people have wondered, where have these things come about? And this is the topic of our today's talk. And believe it or not, even this question is already a lot of progress, because for a long time, the question was not how do stars form, but whether they form at all. So of course, since antiquity, people believed that stars are eternal. But even until the 1950s, the prevailing idea was that all of the stars had formed after some initial point after the beginning of the universe, billions of years ago, and no star formation has currently been happening. So there were a few key observations that led to the whole field of star formation, and due to lack of time, I'm only going to talk about actually one of them. One of the key observations that led to the belief that even in today's universe, stars are actually forming was by this Soviet scientist, Viktor Ambatsumian. And in 1949, he found that the age of some OB associations, so don't get afraid of the name, these are just the name of a star cluster or a group of stars. So, and you can estimate what is the age of a star cluster, because it's an n-body system. And it turned out that this age was estimated to be around only 1 million years, which was much less compared to the estimated age of the universe, which even then was around 3 billion years. So this meant that stars, at least some stars, must have formed very recently. There were other key observations, but and theory, but this was kind of the indirect proof that stars had formed. And the first direct proof, believe it or not, came as late as 1967, where two scientists, Becklin and Neugebauer, they did an infrared study of the Orion Nebula from the Mount Wilson telescope. And what they found was quite interesting. So they found there was a source in the infrared which had no optical counterpart. So this is a picture from their paper. And since their picture is not very clear, I kind of zoom in a bit. So they marked this region, which is marked with a black circle. And they said they found an infrared emission from this region, which corresponded to a black body of around 700 Kelvin, but there was no optical counterpart. And their conclusion was that inside the Orion Nebula, there must be a very cold star or a star that is forming. So this was actually the first observation of an actual star forming, the first proof directly that there is around us stars forming even today. And this was kind of the black body they saw, which with the peak of around 700 Kelvin, or let's say 1,000 degrees Celsius, right? So this is how kind of historically the field of star formation started. But if you feel a bit lost, don't worry, we will go a bit more into detail. So the way I'm going to progress in this talk is that it's divided into 3 parts. So first, we will start with a very simple theoretical understanding of how stars can form from interstellar gas. And then we will discuss some problems with this idealized scenario. And we will look at some actual observations which show these problems. And then we will try to modify our simple model to come up with at least part of the solution. And this is the part I will also then try to connect to my own research. Yeah, so these will be kind of the 3 parts. Okay, so how do stars form? You have a star and we want to know how these stars form. And from what we saw in the figure played before, we saw a star forming inside the nebula, or these gaseous nebula, or what we today call molecular clouds. So let's say a molecular cloud is forming a star here. But what exactly is a molecular cloud? Is it just some patch of light in the sky? Well, no, it has a very kind of concrete description. So normally, if you point at the sky with a telescope, you cannot see it with the naked eye. You can notice certain patches in the sky where it's kind of dark and no stars are visible. So you have a whole lot of stars around, but suddenly, as if there is a dark patch. And scientists soon realized this is because these entities are essentially cold gas clouds, which are quite cold, 10 to 50 Kelvin. They're molecular, filled with molecular hydrogen, and they're reasonably large, so 10 to 200 parsec, or in light year terms, let's say 30 to 500 or 600 light years, which means that the sunlight would, so any light would take a few hundred years to go from one side to the other. So they're quite large compared to our everyday standards, but nonetheless, they are not really, I mean, compared to astrophysical standards, they're quite normal. And they are quite massive. They can be from, let's say, 10,000 to 10 million solar masses. And we said these are dense cold clouds, but when I say dense, this is a very relative term. So the density of these molecular clouds are around 100 particles per cubic centimeter, which is much less dense than the best vacuums we have been able to create on Earth. So it's a very relative term, okay? It is dense compared to the rarefied medium surrounding it. For example, if you take a space shuttle from Earth and you go to space, and you just check what is the density in the space around us, it's around 1 particle per cc. So these structures are around 100 times denser than that. But nonetheless, it's quite rare. So you can think of it like this. Let's say you weigh 60, 70, or 80 kilograms. And if you were suddenly to be turned into a molecular cloud with the similar densities, you would have the size of around the Earth. So take it with a pinch of salt. It's quite related. Okay, so what is the problem of star formation then? The problem is that we know stars form inside this. So we saw one photographic plate image, but I will also show you some actual observations, more modern observations. So we start with something that is cold and with 100 particles per cc, and we need to end up with something that is like the sun, which is of the order of a few thousand Kelvin in the surface, completely ionized in plasma form, and has density around the density of water. So a few times 10 to the power 23 particles per cubic centimeter. So we need a physics that will explain from the left to the right a physics that describes 21 orders of magnitude consistently across all scales. So this is the problem of star formation that we're going to tackle, right? And in a sense, we don't need any very new search of physics. So we know that the physics we need here is Newtonian. We don't need general relativity. We don't need even special relativity. And even quantum mechanics for the gas dynamics, we don't need. But nonetheless, even with Newtonian physics, the problem is quite complicated. To draw an analogy, imagine you are building a cake, you're making a cake. You have never made cakes before. You have no idea how to make them. You tried this cake at a friend's birthday party a week ago, and it was quite nice. And the friend told you what you need to make this cake, the building blocks. You need milk, flour, eggs, but you don't know in what mixture to mix them. You don't know whether you need to bake it, fry it. What do you need to do? So the problem is quite complicated, right? If you just mix flour with milk, it's not going to give you cake. So we need to understand these kind of things. We know the building blocks. We know the essential basic physics. But nonetheless, we need to describe a very complex and complicated system. So this is where the difficulty comes from. So let's dive straight into it. Let's start with a very simple model. Start with as simple as possible. Imagine we have a molecular cloud. We said it's surrounded by a rarefied medium, right? So pardon my drawing skills, but let's imagine this is our molecular cloud, which is set in a rarefied environment, and everything is in pressure equilibrium. It's sitting pretty. This is roughly spheroidal, let's say, is uniform density. And we want to know, okay, it's fine, it's stable now, but under what condition will this molecular cloud collapse? Because remember, we need to climb 21 orders of magnitude in density. So the cloud needs to collapse if it needs to form anything at all. So let's say we give it an initial perturbation, something like a disturbance, can be anything. For example, a supernova shock hitting the cloud, or can be some internal instability, can be many things. And we want to know under what condition this perturbation will make this cloud, either part of it or the whole cloud, collapse. So anytime you give a perturbation to a system of fluid like this, it will create sound waves, right? You see this everywhere. If you hit a musical instrument, that's why the sound is produced, because you form waves. But of course, the normal sound waves we see every day, they do not make a structure collapse. So we need a condition on the cloud that will make this cloud unstable to certain kinds of perturbations. Okay, so let's see how can we define these conditions. We start with very, very general conditions. Consider that the radius of this cloud is r, or can also be a part of the cloud, and its mass is m and temperature T. We say that this cloud will collapse if, due to its collapse, its total energy is decreasing. It's a very reasonable physical principle, right? So this cloud will collapse if, after collapsing, its total energy change is negative, if it releases energy. And the total energy, we can divide it into two major parts. One part is the gravitational energy. So it's a ball of gas, so it has some self-gravity, and it will have some pressure volume work due to collapse. Like if you compress a gas, of course you need to work against it. And we need a condition where the sum of these two would be less than 0. So the gravitational self-gravity of this molecular cloud would be given by this, considering it is spherical in shape and mass m and radius r. This is just 2 lines of integration, but you can imagine, apart from the 3/5, this is kind of what you expect for the energy. And the pressure, if we assume it to be an ideal gas, is given by the ideal gas law, where m bar is the mean mass of a particle. So if this cloud is fully molecular hydrogen, this m bar would be twice the mass of proton. Since there is some helium involved, it's usually a bit more than 2. And we put these gravitational energy and pressure into this inequality. And we want to get a condition for collapse. So this is some bachelor's level physics some bachelor's level analysis we do here. And what we get is called the Jeans criterion for collapse. So forget all the maths. It can be expressed in terms of mass or density or radius. I'm going to do it in terms of density here. So this inequality, what it says is that if we have a cloud of mass m, it will collapse if its density, consider that we use the uniform density, is greater than some critical density. And this makes sense, right? You have a ball of gas which you want to collapse on itself. So the more dense it is, the more likely it is to collapse. So we should have a critical density. And this critical density, if you put in the formulas, it gives something like this. The exact form is not really our concern, but you can see that there is mass and temperature inside. And if we put values of typical numbers for molecular clouds, so temperature of 10 Kelvin, mass of, let's say, 10,000 solar masses or a bit more, you get that this critical density for a cloud to collapse is around 1 particle per cc. And as I also showed in a previous slide, from observations, we know that the typical molecular clouds have densities of 100 particles per cc. So our analysis says that our cloud should collapse to form stars, which is great, which is what we want, right? If our analysis told us that, okay, everything you see, it's super stable, it shouldn't collapse, then we couldn't form stars at all. So this is what we want. We want our clouds to collapse. Okay. Now what happens, let's say it starts collapsing, what happens then? So initially when this cloud is collapsing, its temperature does not increase. This is a bit counterintuitive. So normally if you have gas and you compress it, its temperature increases. This is, just think about when you're pumping air into your bike. You're compressing the air and it gets warm, right? But because the molecular cloud is rare enough, because it has densities of only around 100 particles per cc, this radiation, the radiation manages to escape. So initially, the cloud does not heat up and begins to collapse. And it can also separate into different fragments. It can fragment during this collapse, and each of these fragments continue collapsing on the way. So in the next slide, I'm going to show you a video of one such fragment. We call them a molecular cloud core. So imagine we have a molecular cloud core like this. Its radius is around 0.1 parsec or 0.3 light years. And we start with very simplified conditions. It's uniform density, and it has a turbulent velocity field. And we let it evolve. Let's see what happens here. So it's collapsing. You will soon see some structures forming. And then look out for a black dot in the middle. Soon it will collapse. And there you see a black dot that is forming in the middle. If I pause here for a bit, so this is what we call a protostar. So the central part of a molecular cloud core, it reaches hydrostatic equilibrium at some point, which means its pressure gradient equals the gravitational pull. So it begins to collapse very slowly. So normally the molecular cloud is collapsing reasonably fast, but the core is collapsing slowly. And also, this is a bit larger. So our sun was also once one such protostar, and you can see the red part around it. It's what's called an accretion disk, which forms due to angular momentum conservation. And this disk supplies gas onto the protostar. So initially, this central protostar would be much less massive than the sun. So for example, when the sun was a protostar, it was not one solar mass. It was much less. And then it was fed mass through such accretion disks. Okay. And this accretion disk is what in the end forms planets. So it's in the advanced stage of an accretion disk. The gas is stripped, the gas is gone into the star, and what is left is a protoplanetary disk, and this is where planets come from, which is of course a problem more of planet formation, but it's also very interesting. And I show very nice observations. This is from ALMA of a star HL Tauri, and you can see the protoplanetary disk. So this accretion disk that we see in our simulations, we can also see them in real observations now. And this is a bit more advanced stage. So these black tracks you can see here, these are signs that planets are already forming. Okay, so what is the picture we have so far? I have given you some information. So let's take a step back and have a look at what is happening. So we started with a molecular cloud here. And I did not tell you how it comes around, but it comes around from the more diffuse medium, right? It has to. And then this molecular cloud begins to collapse, and it can form one or several, usually several protostars, each with their accretion disk. And these disks, when they get depleted of gas, form the planetary system around the star, such as the sun and all the planets that exhibit today. And then something happens, why the title also is called the molecular cloud life cycle, but we will come back to that. So these are the stages we look at right now. And to be honest, even though it's very simplified, the kind of overall picture holds more or less true, especially for low mass stars. For high mass stars, there are more problems. But okay. But what are the problems with this scenario? So we will discuss some actual observations, but before that, I think it already really helps if we simply look at some actual star forming regions to see how a star forming region looks like. We made all these assumptions, right? Spherical, uniform density, and you can probably already guess that they don't hold very well, but let's just have a look. So let's start with something very familiar, something we see for half of the year in the sky, the constellation Orion, or in Bengali, as we say, Kalpurush. and we look at its same counterpart in the ESA sky map, which is an amazing website. If you don't know it, I suggest you play around with it. It's really nice. And we identify the same regions. So you can see the belt of Orion and also Betelgeuse, or what in Bengali we call Adra here. And today we're going to look near the belt of Orion, near the star Usha. So we zoom in a bit, and here is the belt of Orion that you can see. And already you can see some very interesting regions. So the bottom one is Orion Nebula, and the top one is region called Orion B. Astronomy pictures of the day all the time. So here is the Horsehead Nebula, for example, and also really, really interesting region by itself. But for today, we are going to concentrate in the other region, the Orion A and the Orion Nebula. Remember, this was also where the first protostar we saw with the 1967 paper was seen. Okay, so let's have a closer look. This is an image in optical of the Orion Nebula. So the glow here comes from the stars in the trapezium cluster. But to me, at least, there are some interesting features. But for star formation, this picture doesn't tell us so much. But if you can guess what is coming, you already can see that there are lots of regions where there seems to be dark lanes. I don't know how good the display is, but I think you can probably see. And now we look at this same region, but we just change the wavelength. We look at the same region and we just change to infrared. And this is what you see now. And suddenly there seems to be a whole lot of different other things. And this is just a screenshot again from the ESA sky map. And everything you see here is star forming gas in kind of this reddish color. And so this is just a screenshot, but we have a bit nicer image. So I go to the next slide, and this is an image from Herschel that you see of the same region. So this Orion Nebula we see are essentially these two white glow regions where the star forming gas reflects the light from the trapezium cluster. And everything you see here, this kind of shape, is star forming gas. And every bright dot you see here is one protostellar system or multiple protostellar systems, such as who we have shown before, like this star with this protostar with the disk. So you already begin to see some of the problems. So we assumed it was spherical or spheroidal at least, but if anything, I would call it more filamentary or snake-like, right? And this whole region is something like 30 parsecs across, or 90 light years. So it's quite large. And also, although this is a column density map, you can see that the uniform density assumption doesn't hold anywhere near true. Even within subparsec to parsec scale, you can see great differences in density contrast. The whole thing is incredibly complicated. So our assumptions are already very weak for this model. And it just doesn't stop there. We can look at some actual problems with our scenario. So let's see that. I will discuss two problems. The first one is as follows. So our scenario said that we have a molecular cloud which is collapsing to form stars. So if the gas is moving like this, as for collapse it should, then you should have, so let's say you're observing a molecular line from this region, a CO line emission or something like this, then the gas which is moving away from you, its emission should be redshifted, and the gas that is moving towards you should be blue shifted. So even if it's not so extreme, you should have a characteristic shape for this global infall that the model predicts. But there is no such clear observation of a global infall. So we need to explain this absence of global collapse signature in observations. And there is a second problem. So in our model, we saw that this whole molecular cloud was collapsing to form one or a few stars, right? This suggests, so I didn't do the math, but you can actually see that most of the gas mass should end up in stars in this way. But it turns out that no matter how many molecular clouds we see, and we have a lot of them in our Milky Way, so we can observe them, and also, of course, other galaxies, but they're harder to observe. And we see no matter where we look, on average, only 1% of the molecular cloud mass is in actually stars, and 99% of the mass is in gas, which will never end up in the stars themselves. So star formation is incredibly inefficient, where 99% of the gas of the parent molecular clouds never actually end up forming stars. So why is star formation so inefficient? So any model that we need for star formation, for this part at least, needs to explain these two key observations. I mean, there are more, but we stick with two here. One is that why do we not see global infall signature? And second is, why is star formation so inefficient? Okay, so we need to modify our model. It had some nice perks, but we need to change it. And I'm going to discuss two different models for this scenario that are very much in discussion even today, especially today. So the first one is the gravo turbulence scenario, which combines gravity and turbulence to explain this. So I will briefly talk about what is turbulence. So turbulence is kind of so it's a kind of motion which is not laminar or not regular, and where you have eddies across different scales. I will not go into the details, but we have an intuitive understanding of turbulence in everyday life. If you just open a water tap, you will see initially the water is flowing very smoothly, but then it kind of roughens up. So this is a transition from laminar flow to turbulent flow. In cigarette smoke, when it is rising, you can also see it where the initial few centimeters would be laminar, and then the motion becomes very complicated. And also it is seen in a lot of art, such as Van Gogh's famous Starry, Starry Night, where he kind of shows these motions. But the important point I want to stress is that turbulence in a fluid can generate support against collapse. Imagine you have a muddy water, and if you just let the water stay there, then the mud settles at the bottom. Now, if you're stirring it continuously, then the mud will never fall due to the gravity itself, right? So it will get support against gravity. And something similar can happen in molecular clouds. So the gravo turbulence scenario says is that, well, molecular clouds are highly turbulent, and there are observations to kind of support this, and that they are not globally collapsing at all. So we do not see global collapse signature because they're not collapsing, but that they are supported by this kind of turbulent pressure. And where this turbulent flow converges, so where multiple eddies converge, you have an overdensity, and some of these overdense regions can become gravitationally bound, and when they become gravitationally bound, they collapse to form stars. And if you're interested more in this topic, this was one of the first papers that discussed this. And this is another key paper, review paper, which also has discussions on it. And we kind of accepted this. But for a few observations that could not be explained, at least in this form of the model, there have been other models coming up. And one very interesting model is a rehashed version of the global collapse scenario that we talked about before. And this is now called the global hierarchical collapse. So in this model, what is happening is saying molecular clouds are gravitationally collapsing, but they are collapsing gravitationally on every scale simultaneously, but this collapse is very chaotic. So you do not have a spheroidal cloud, maybe you have a very filamentary structure. So the collapse is kind of really chaotic, and this erases any signature you would expect from this blue shift, red shift global collapse argument. So you can imagine that globally the cloud is collapsing very slowly, and inside, so the smaller, denser structures are collapsing much faster. So it's kind of like a rehashed version of the global collapse scenario we initially discussed, including turbulence and a lot more nonlinear physics. And then it says that, well, of course, the cloud, if it were allowed to collapse completely, it would have formed probably 90% of its mass into stars. But massive stars form very fast inside the cloud, and these massive stars disperse their parent cloud by terms of wind or radiation. And I will show you a movie about this from my own simulations. And these this disperses the cloud before the cloud can collapse totally. So that's why the star formation efficiency is very low. If the massive stars didn't, ionize everything and destroyed all the molecular hydrogen, we would have had a very high star formation rate, but this doesn't happen because the cloud just dies before that. So, and if you want to know more about this scenario, this paper came out last year and it discusses this really nicely. And so if we compare the two scenarios here, so they explain the observations as follows. No global infall signature is seen. So according to the gravo turbulence scenario, this is because, well, the cloud is not collapsing, so there is no collapse signature. And according to the other scenario, it is because the collapse is really chaotic and this erases all signature. And star formation efficiency is low because according to the gravo turbulence scenario, so you can imagine that there are only these turbulent eddies which collapse, which kind of converge. So it's a kind of a random event and unlikely. So that's why it's just very unlikely that parts of this cloud would become dense enough to form self-gravitating bodies that will end up to form stars. And according to the global hierarchical collapse scenario, as we discussed, this is because the cloud is dispersed before it can really contract very much. And my work, essentially what I do is to try to distinguish between these two scenarios. At the moment, what I'm trying to do is that I'm trying to distinguish between these two models of how we go from a molecular cloud to a protostar, or at least a bit larger structures, and which model is supported in terms of simulations. So before I go to a little bit about what I am doing, just to kind of give you a very brief overview then of the complete cycle, which also we can connect with this feedback. So we start with this molecular cloud, which collapses, as we said, and this collapse can be very chaotic, or it can collapse just in parts, according to the turbulence scenario. And these dense parts then form these stars with accretion disks, and then they deplete the gas to become these stellar systems. And the massive stars, this is where it's important, they are always radiating energy. So massive stars are really luminous, so they're radiating a lot of ultraviolet light, and this can ionize the molecular hydrogen, right? So if your molecular hydrogen is gone, then you do not have a molecular cloud. And also there is stellar wind feedback, which can push the cloud away, for example. They can also explode in supernovas, and this can also destroy the cloud. So all these effects eat away at the parent cloud themselves, and the cloud again becomes diffuse, neutral, or ionized hydrogen. And then again, due to some mechanisms, which I'm not going into, but you can ask me if you're interested, again, at some point it will form another molecular cloud. So this is kind of the molecular cloud life cycle, where if we start with a dense molecular cloud, we will form stars, and the stars will kill the molecular clouds themselves and go to diffuse medium, from which again we may form dense molecular clouds. So star formation and the molecular cloud life cycle are very intrinsically linked. And the detailed part where we discussed a bit more, where discussed these two possible scenarios, the gravo turbulent and the global hierarchical collapse. And so as I said, my work is to try to distinguish between these two scenarios. And I do this under the SILK project, which is kind of the flagship project of our group, which is called Simulating the Life Cycle of Molecular Clouds. So as you can imagine, it's about the life cycle of molecular clouds. So what we do is we take a region of the galaxy. So usually it's 500 parsec times 10 kiloparsec in the vertical direction. We start with a galactic disk and we just let it evolve with supernova and so on, and we see what happens. And so you can see the density here, the column density, gas is being blown apart and then it again falls apart. But we can look at various different things, but what I want to draw your attention to is that you will also see, so we can trace this with the with the chemistry of the gas, of its reactions, that you see molecular hydrogen actually forming here, right? So these are signs where molecular clouds can form or are forming. And this is what we want to study in the next project, which is called the silk zoom. So we zoom in on these certain regions. So we run the whole box and we run these regions with a better resolution. So these look something like this. So it's like a slice of the galaxy. So I'm just showing you the disk. And these larger boxes you see, these are where we run simulations with a higher resolution to really get down to better densities to see actually the protostars forming, well, kind of. And these blue dots you see here are these protostars. And we analyze these regions. And my current work is that I analyze these different clouds and try to see which of these two scenarios of fragmentation of energy flow we talked about happens. So I think the best is I just show you a video of this. So we so any of these zoom in regions that we showed, if we use like a 3D volume rendering to show how it shows, it looks something like this. So you see very filamentary structures, which we also see in observations, even if not exactly like this. They are 30, 40 parsecs long, and in central parts there are stars. And if I let it evolve at some point, you will see that so stellar feedback, so these massive stellar feedbacks we talked about is destroying the filaments themselves, the whole molecular cloud itself. So you can again see the kind of observations we talked about. We can actually see them in our simulation somewhat. So I will play this video once again so you can see this molecular cloud. Sorry, the video is a bit jumpy, but these pictures take time. And it's for around 2.5 mega years that this simulation I'm showing you. And you can see the molecular cloud getting destroyed again. So that's kind of my work. And I can go into more detail if you want, but not at the moment. And so just to kind of conclude, and then I want to end with some open questions. So we started with a very simplistic view of star formation. We looked at the Jeans criterion to how a molecular cloud can collapse to form stars. Then we looked at an actual star forming region and kind of saw what were the problems with this. And then we tried to modify our initial model to account for this. And yeah, then I tried to show you at least a little bit of how modern simulations work, or how I am working on this. And finally, I would like to, so this was only a little part, right? So in the molecular cloud life cycle, this was this little part. So I want to discuss a few more questions that are kind of open questions in the field of star formation, in that we know some ideas, but we still don't know a lot. So the first one is, of course, the question we discussed in a little bit detail, is that why is the star formation rate so low? And why is it around 1%? Does it vary from galaxy to galaxy over cosmic time, and so on? So this, we have some models, but also there are many things we don't understand. The second one is that not only, so I told you that around 1% of the gas mass ends up in stars, but turns out that not only that, the way this mass is distributed among the different stars is also kind of universal. And this is something called the initial mass function. Without going into any detail, it's something like this. So if you have mass on the x-axis and number of stars with that mass, no matter which molecular cloud you look at, it always has this characteristic shape. This is a power law tail, since this is a log-log shape. And it has a power law of minus 2.35. So this means that higher stars, so massive stars are much rarer than low mass stars, which makes sense. And then at some point there's a bump. But it doesn't explain why in every molecular cloud we see that the same power holds, that the massive stars are exactly as rare or within observational limits. Why is that, and what determines it? So this is not well understood. Another question is, of course, the formation of molecular clouds. We have some ideas about how the molecular clouds form, but it has to do with a lot of detailed chemistry, from transition from atomic hydrogen to molecular hydrogen in such conditions, and we do not understand a lot, and there are conflicting scenarios for that. Another big question is, of course, the role of magnetic fields. If you're in astrophysics at some point in life, people in conferences or anywhere will, at the end of any talk, will ask you, what about magnetic fields? And star formation is not different. So if we look at star forming regions, so this is the same Orion region, just that the resolution is not high enough. And from dust polarization observations, you can see magnetic fields. And these kind of contours you see, so these kind of lines, these show the direction of the magnetic fields, at least in the plane of the sky. And we know they're there, and we know they should affect the gas, but we have some idea about how, but there's a lot of things unknown. And another question is, of course, the nature of turbulence. So the turbulence we use is incompressible isotropic turbulence, but you can imagine if magnetic fields are present, then there is direction. Turbulence is not isotropic. So again, we need to incorporate magnetohydrodynamic turbulence, and we just don't talk about it in the field. We just assume that it works. So there's lots of questions, and if you want to know more, I give a few literature you might be interested in, and with that, I think I will end my talk. Thank you.
Thank you so much, Shashwata. It was wonderful talk. So we already have a lot of questions, but I want to just mention that if you have any question, please raise your hand, write your question in the chat box. So we have now 3 questions from the Achoda asks, hello, am I audible?
Yeah, I think my internet was having a little bit trouble, but keep talking. I should stop sharing the screen for now, and then I'll share again after the question. Please ask.
All right, thank you. So Atul says, what does viscosity mean in the context of molecular clouds?
Sorry, can you repeat the question? I think my internet is having some problem.
What does viscosity mean in the context of molecular clouds?
Right. Yeah. So it's typically, so it depends a bit on the mass of the molecular cloud, but it's a few mega years. So let's say 2 to 5 mega years, something like this, maybe 10 mega years. So there's also a little bit question. Some people think it's really transitioning objects, so they only last for, let's say, 2 mega years or something. But there are some people who think it lasts around a bit longer, but a few mega years is typical. Was that understandable?
Hello.
Hello.
This is Sotan. I think I said asked about viscosity. You answered another.
Yes.
All right. What does viscosity mean in the context of molecular clouds? Sorry. For most astrophysical purposes, so viscosity is of course important, and viscosity is there, and but for our kinds of simulations, we usually do not consider viscosity, because viscosity is important when you are in relatively dense environments. So for example, in planet formation, viscosity is really, really important. But for most of, so if you're in, let's say, 1 parsec scale, sub-parsec scale, or even if your simulation is a few hundred parsec scale, the effect of viscosity is really low. Of course, physically speaking, what viscosity, it does come into effect at some point where it destroys the turbulence and creates some random field. But for most of the molecular clouds, for most of the length scales you're interested in, you don't really need to think about viscosity. It's when you're going into these really dense regions, so I would say maybe 10 to the power 13, 14 particles per cc, probably even more, that, and then you really need to think about your viscosity. And the reason for this is as follows: because in most of our simulations, the numerical viscosity, so if you have a code, it has a numerical viscosity, which is kind of the limit of your code, and this dominates any physical viscosity. I cannot quite hear. I'm not sure exactly why. Can you repeat the question?
Hi, Shashwata. I think someone just unmuted them mistakenly. Sorry.
Okay. So what's the next question?
Yes, so Pritham Manna says, other than the gravo turbulence or the global hierarchical model, does there exist other models which effectively predict similar behavior?
Yes. So for a long time, until the 90s and even early 2000s, magnetics. I didn't talk so much about magnetic fields, but people thought that molecular clouds are not collapsing because of magnetic fields. Because magnetic fields can provide support. So if you look at the equations of magnetohydrodynamics, you can derive a magnetic pressure term, so similar to just how a gas has pressure due to its temperature, so it can also have pressure due to its magnetic field. And people thought for a long time that this can really explain why molecular clouds are not collapsing, or at least not globally collapsing. But there were some observations which kind of made this out of favor. One of this was that we found that despite the magnetic fields, clouds should still collapse. So this was one theory which was really, really popular for, let's say, 15, 20 years. Recently, there has been another model called the bubble-driven filament scenario, which really focuses on the anisotropy of the cloud. So it says that when the cloud collapses, it forms really like filamentary structures, and then it creates H2 regions. And this is also kind of is another scenario that is kind of emerging to explain some of the deficiencies of other models. The truth is probably, as always, somewhere in between. But there's a lot of different ideas even now, and it's a very active question.
Okay, so the next question is from Olonka Datta.
Mm-hmm.
He says, does this simulations use finite volume?
So different simulations can be used. So the last movie I showed you, it was indeed a finite volume simulation with the code Flash. There are also SPH simulations. So this molecular core collapse I showed you was done with an SPH code Gandalf. One can also, there are lots of different new codes people are using. So there's moving mesh, there is meshless code, which is what I worked with in my master's. But in my work group, we still primarily work with finite volume codes.
Okay, thank you. Obhinandadi says, how much time does it take to form stars from molecular clouds in general? The simulation you showed first had a parameter t.ls. Has a parameter t. Is that the time? Then what is its unit?
The unit there was megayear, and typically from a molecular cloud to star formation takes around one free fall time or something like this. So if you have a gas and you can estimate if this gas was kind of ideal, after what time it would collapse, and you come up with something called the free fall time, which is proportional to 1 over square root the density. And if you put these values in for typical clouds, this comes to, let's say, 0.1 megayear to a few megayears. So less than 1 megayear. So the first stars should form at, let's say, after 100,000 or a few 100,000 years after a molecular cloud forms.
All right. Okay, so there are several hands raised also. So Ashif Akram, you can unmute yourself.
Yeah, Shashwata, খুব ভালো talk. So my question is related to the Jeans criterion for collapse. So you said that the rho has to be greater than 1 part per cc for the collapse to happen globally, right? So now we know that even now there are many interstellar medium where it can go beyond 1 part per cc.
Yeah.
Why a new protostar is not and in many cases protostar is not being formed there. So what could be the possible reason, and how much we should rely on this Jeans criterion, because you also said about some of the molecular clouds which has 100 per cc and still not very efficient. So can you just elaborate on this?
Yeah, so of course, you know, the Jeansaw criterion you should take as a ballpark estimate, not something exact. And to answer your question, there are two parts. One is that, so the Jeans criterion has the temperature inside it, and this is very critical. So if you have any space which is not molecular, so let's say if you just go to the space outside in the solar system and it is 1 particle per cc, why is it not collapsing? Because the temperature is much higher. You need a very cold gas for it to be 1 particle per cc. If you have like ionized gas or hot gas, you will see that this goes up to, I don't know, 10,000, 100,000 particles per cc. So that is why outside cold molecular gas, stars cannot form, because just by genes, if you just put in the typical values of temperature, you will see those are much, much higher they become. So you really need this 10, 20 Kelvin temperature. And the second is inside the molecular clouds themselves, of course, the genes, we didn't include a lot of physics, right? So we didn't include turbulence, we didn't include magnetic fields, and these kind of things can really alter it. So the genes should be taken as an order of magnitude estimate, that, okay, if something is, let's say, 2 orders of magnitude less than the genes, then it's definitely not collapsing. If it's 2 order of magnitude more than the genes, then it probably should collapse unless there's something super strong. But so it's a kind of convenient analytic expression for us to understand, but nothing exact.
And if I want to understand the equation of state of the molecular cloud, normally we take non-relativistic particles to have zero pressure, right? Pressureless kind of dust, right? These molecular clouds. So in that case, the P del V that you have talked about, that does that contribute much? Basically, you are saying that the gravity is anyway negative, right? So so this P del V, how does it contribute?
The thing is that the thermal pressure usually is not so much, but it is not exactly zero. So please do not get confused with that. Of course, when we talk about cosmological simulations, then it is 0 to a limit. But of course, it has some thermal pressure, which is negligible normally. And also for most star formation problems, it's also not that much. So the PdV term that comes from the temperature is in most cases not that significant. I hope that answers your question.
Right. Okay, so let others ask questions.
Thank you. Alumni, you are next. Please go ahead.
Yeah, am I audible?
Yeah.
Yeah. So thanks. It was a really nice talk. So I had a couple of questions. So first one is, you had what kind of radiative cooling do you assume? Do you assume some kind of a collisional ionization equilibrium for the gas, or what kind of radiative cooling? And is photo heating, like say from a hot mother or something, is important here as far as dispersion of this molecular clouds is concerned?
So in terms of the cooling, we have something called the non-equilibrium chemical network, which does not assume any collisional equilibrium. So this is really required when you want to capture the dynamic chemistry. So we have this included, and our simulations are one of the few actually that do have it. So that is this, and you use non-equilibrium cooling for this. In terms of
you don't have any. Please
sorry,
go on.
Yeah, in terms of photoionizing heating, yes, it is included. So ionizing radiation. So there was a paper from our group a year back, which was the first to show in this field the relative importance of photoionizing heating and, for example, stellar winds and so on in terms of dispersing a molecular cloud. So you need to consider different things, including radiation pressure, including photoionizing heating, including stellar winds. And ideally, you should include all of them, but of course, see, then it becomes really expensive. So you have to.
Sure. And I see also that there is generation of angular momentum. So is turbulent vorticity is what you rely on to generate this angular momentum?
You don't really rely on, so the idea is that you generate angular momentum just by the virtue that it is collapsing, right? So angular momentum is, let's say, m omega r square, something like this. So if you have a cloud, let's say it's going from 1 parsec to point, I don't know, 10 to the power minus 3 parsec. So its radius is decreasing by 3 orders of magnitude, let's say. Then by conservation of angular momentum, you should have increase in omega of 6 orders of magnitude, right? So even if you have a so you just have a turbulent velocity field and almost everything cancels out, but just a little bit doesn't. So you have a very little initial omega just due to the fact that in a random field, not everything cancels out. And just by the fact that it is contracting, this omega will be amplified by 6 orders of magnitude, in this case, even more. So that's why you see this disk forming. That's why you see the angular momentum actually in action.
Thanks. Thanks a lot again.
You're welcome.
Thank you, Alankar. Kaustubh, please go ahead.
Hi, Shashwata. Thanks for the very nice talk. I have many questions, but I'll stick to one for now. With the so there you discuss about two scenarios. One is driven mainly by turbulence.
Yeah.
The other is a rehash of the overall collapse scenario.
Yeah.
Where it explains the low efficiency by putting in the fact that due to feedback from the first formed high mass stars, the cloud itself disperses or something like that.
Yeah.
So I have two main questions regarding that. One is, how do you explain the huge mass that forms in the form of low mass stars because of the initial mass function? So high mass stars are pretty rare. Most of the mass is in low mass stars. So how would you explain that in that case? Because they shouldn't disrupt the cloud while forming. And how do you explain the wide variety with that? How do you explain Milky Way like star formation efficiency and say a starburst system where the star formation is several orders of magnitude higher? So that very wide variety of star formation rate, isn't that contradictory to that model?
Yeah, so what they include a critical thing, which is that they say that it depends a bit on the surface density of the galaxy. So if we imagine the galaxy to be a disk, right? So where you have a high surface density of gas, this is like the galactic sector, for example, or in a starburst galaxy, you would expect more star formation. So they include the possibility that where you have relatively low this density, there they say that probably the turbulent model is more likely. But what they're saying is when you have a high, so I don't exactly remember the numbers, but when you have a relatively high surface density in the galaxy, this is where gravity has to be more important. And this is what you see. And the wide variety is explained also in terms of turbulence seeds. So the main difference from the traditional version is that they also try to explain how turbulence plays a role. So turbulence makes the exact shape of the cloud or where the clouds can form. And this can explain a lot of things. For example, imagine you have a massive star forming at the edge of the cloud. So then its H2 bubble or H plus bubble will not disrupt the cloud so much because a lot of the effect will just, go out. So the fact that the geometry or the structure is determined by the turbulence. So the turbulence kind of guides the exact way in which the cloud disruption would occur. So that's their explanation for the wide variety as far as I understand.
Okay, thanks.
Thank you, Kaustubh. Deepta, you're next. Please go ahead.
Shashwata, so my question is about the turbulence what you talked about. So the question is, so when you do the simulation, you start with some density, something like 100 particles per cc. So so from the starting you switch on the turbulence, or after a while you switch on the turbulence? Because if this number is very small, then that would be difficult to have turbulence from the very beginning. So is there a threshold to switch on the turbulence?
So in simulations, you typically have different kinds. So there is something called a turbulent box, where so you just have like a simulation box and you just have some gas and put lot of turbulence, and sometimes you keep driving this and you start with an initial density of rare gas. So if you want to form molecular clouds which have a density of 100 particles per cc, you typically start with 1 particle per cc, because this is where you want to get molecular clouds, right? You don't want to do this. Also inside molecular clouds, if you want to go from molecular cloud to star formation, you just initially start with a turbulent field and you don't continuously generate it, because then it's artificial, for example. There are also other kinds. In our types of simulations, the ones I showed, the turbulence is self-consistent in the sense that we don't artificially drive it. We just let the stars evolve with their feedback and blow up in supernovas, and this generates the turbulence in itself, so in a more self-consistent manner. So of course you have less control then over the turbulence, but it's then not put in by hand. So that's the benefit of that.
Thank you.
Yeah.
Thank you, Rita. Ochishma, please unmute yourself.
Yes, can you hear me?
Yeah.
Yeah. So thank you for the very nice talk. I'm Ochishman from UG3. So I had basically a question, perhaps I missed this. Can you just give me a brief idea, I mean, just qualitatively, about how the magnetic fields can influence the star formation activity? I mean, you just said that, well, magnetic fields play a role in all this stuff, but you didn't really go into the details. So can you just give me a qualitative idea? So,
yeah, sure.
Yes.
So it depends a bit on the length scale you're talking about, and the effect changes, but the essential feature still stays the same. So there are a few critical effects. One effect is that magnetic field can redistribute angular momentum. So this can be really, really important, because if you're so what you see is that stars have much lower angular momentum than molecular clouds or accretion disks. So somehow you need to get rid of this angular momentum, and magnetic fields can do this because they have Alvin waves essentially, and this can redistribute the angular momentum. So this is one way. Another way is that if you have, let's say you have magnetic fields, then if you imagine as in a plasma, along the field lines, charged gas does not feel any force. So gas can move easily along the field lines, but perpendicular to it, it cannot move very easily. So if you have a structure where magnetic field is somehow artificially or something in one direction, then gas will preferentially collapse along that direction. The shape of the collapse structure, for example, and also determine its dynamics. And then it can have pressure which stops the structure from collapsing at all. So there can be lots of different effects. It depends a bit on the field strength, but also it depends a bit on what kind of assumptions you're using for the magnetic fields, because observationally, the observationals are very bad in terms of magnetic fields. It's very scarce and there are lots of uncertainty. So we don't know a lot of things.
Thank you. Thank you very much.
Yeah.
Thank you, Chishman. So we have a few more questions in the chat. So Gorima says, if after an initial perturbation, the molecular cloud has started to collapse to form a star, is there any mechanism, another strong supernova shock maybe, which can stop the star formation?
So if the supernova comes from outside the cloud, then no, because then it would rather help the cloud collapse itself. I think the best way is actually that you have some initial massive stars forming and they radiate a lot of energy, and this can kind of either disperse the cloud or stop feedback from forming because it heats up the gas. Because if there's a lot of radiation, it heats up the gas, and this can drive the temperature up, and that can stop, for example, genes fragmentation or genes collapse. So that can happen, and probably does happen as well.
Okay, so the next question is from Orito Kundu. He says, in cosmology, we see filament-like structure formation. So with that picture in hand, why did people not notice the problem with the global collapse scenario before?
Yeah, I mean, they did notice, right? But you do what you can. So I mean, so for example, how so star formation in a filament, uh, it was kind of semi-analytically done in the 90s. Um, but before that, there just was not so much theory. There is a paper in 60s by Kim Ostreicher, which is a kind of seminal in this. It discusses when a filament can become unstable. So people did think about this, but they kind of thought that hopefully this will still hold, even though this is a bad approximation. You know, maybe it can explain the essential features. But this we do in all of physics all the time.
Okay, so Atroda had another question. So what is actually leading to the filamentary structure? Because that means there is some preferential direction.
Yeah, so magnetic fields cause a preferential direction, for example, though it's not always clear if filaments are parallel to magnetic fields or perpendicular. It's also a matter of active research, actually. But also, just in terms of how anisotropic gravitational collapse works, you preferentially would first have collapse in one direction to form kind of like a sheet-like structure, and then in another direction to form filaments. So I think this is the natural progression of anisotropic gravitational collapse, and this we see in all the simulations, just as in cosmology, for example.
All right, so we have two more questions in chat before I can go to Kolkata again and Asif Akram again. So Shrikat Sinha says, what will happen when two accretion disks are close together? Will any star form?
Yeah, can happen. You often, I mean, two protostars with accretion disks colliding, I mean, probably can happen. I don't know how likely a scenario that is. Probably the accretion disks just merge. But what we see really more often is that you have a star with an accretion disk, and this accretion disk becomes gravitationally unstable because it is a disk, and if it has a certain gas surface density, the accretion disk can become gravitationally unstable and form stars or brown dwarfs themselves. So a lot of the binary systems are actually forming in this way. And also there are some theories that say that brown dwarfs like Jupiter, for example, are forming in this way, where the accretion disk becomes unstable and forms stars. And you can also have a binary system, and then they two would share a common accretion disk. You can have like a very tight binary with an accretion disk. And if you have a probably more loose binary, then I think it's harder to have a well-balanced accretion disk because there will be a lot of tidal disruptions. But people who do star cluster formation or some similar or binary statistics, they really have to deal with this a lot.
Okay, so Rudrapriyadi asks, can cosmic rays affect star formation?
Yes. So again, so I told you when I discussed magnetic fields that up until a few years ago, we really didn't have too many simulations with magnetic fields because it was just hard to implement them. So every conference or every talk, people in the end would get up and say, but what about magnetic fields? And I can say in 2020, cosmic ray has taken this place. You go to a conference, you give a talk, somebody at the end asks the question, what about cosmic rays? And they are indeed very important. So cosmic rays are important in two regimes. One is a really rare regime where it's ionized or something, and then also in the really dense regime where the density goes really high up and the interaction probability with cosmic ray can go up. And this can do a lot of things. The first thing is that the cosmic ray ionizes the...
So Kostata had some more questions. So Kostata, please unmute yourself.
No, I think I shall pass. I'll ask Shashwata later. We should respect everyone's schedule. It's way beyond time.
So I'm audible?
Yeah, you are audible. Hello.
Please go ahead. I'll ask later.
Okay, so Ashif Akram has raised hand. Do you have any more questions, sir? Please.
Yeah. So Shashwata, একটা প্রশ্ন ছিল যে ওই মলিকুলার ক্লাউড গুলো যেগুলো স্টার ফরমেশন করছে না কিন্তু মোটামুটি 100 পার্টিকেল পার সিসি এরকম ডেনসিটি আছে, সেই পার্টিকেল গুলো মানে সেই মলিকুলার ক্লাউডটা কি হয়, মানে সেটা কি স্টেবিলাইজ হয়ে ওভার টাইম কোল্ডার একটা ফর্ম নেয় না না ওটা কোনো রকম ভাবে অন্য কিছু ফরমেশনে পার্টিসিপেট করে, what happened to them?
So there are different ideas. There are molecular clouds where there is no star formation happening. And one of the ideas is that these molecular clouds are just very new. So the stars have not started to form. So after a molecular cloud forms, it takes, let's say, 100,000 years before the first stars form. So this can be one issue. Another can be that maybe due to certain specific conditions, maybe they have very high turbulence. So if nothing is forming, turbulence is always a good candidate. Maybe it just has a lot of turbulence, and this is another idea. But we mostly think that if the stars are, we don't see stars, they have started to form yet, but just not in a state where we can observe them. Because, there's a lot of dust, there's a lot of things. It's hard to observe these things.
Okay.
Okay, so does anybody have any more questions? I guess not. So thank you so much, Shashwata. This was